Hello and welcome back to this GPU lecture. We're currently in this rather theoretical part of the lecture where we're talking about the graphics pipeline, and we started at the host interface where the driver passed commands over to the command processor, and then finally in the last session we started talking about how those commands propagate through what is called the graphics pipeline. And we followed the commands, like the draw commands and the data that is passed over by the command processor. We followed it through the vertex stage, and we saw how the pipeline would assemble primitives from that and would clip those primitives against the visible frustum. And then we talked quite a lot about the scan conversion phase and the raster engines that are responsible for generating fragments from the input geometry. And today we're going to very briefly talk about the fragment stage, like the stage where fragments are textured and where they are shaded and where the final color of the fragment is determined, only so that in the next step the fragments are blended and potentially discarded because they're invisible. And the fragment stage, as a matter of fact, we can actually very briefly discuss, because most of what we said about the fragment stage has already been said when we discussed the vertex stage and when we discussed the rasterization stage. Right? Because, at this stage, we have those operations that are concerned with shading and with texturing. And on the other hand, this is another programmable stage. And the fact that this stage is programmable basically means that the fragments are just processed in the very way that we discussed when we talked about the vertex processors, right? So last time we talked about vertex processors, and we talked about how vertices are scheduled in warps, and each vertex processor has a number of cores, and then on each core we can schedule a warp of like 32 or 64 threads, and then each core processes one warp, and that happens concurrently. And then again, each of those processors has many cores, and then there's also a bunch of processors. So we have basically what is massive parallelism, and that massive parallelism now carries over to the fragment stage. Only that the data that we process on the fragment stage is a bit different. Like, the data that we work on is just the fragments that were generated from the raster engines. And this is actually the most important part about the fragment stage, is that it is another massively parallel stage that goes through those unified shader processors, like through those processors that can handle both vertices and both fragments. And the other thing that is quite noteworthy about the fragment stage is the fact that the GPU pipeline needs to maintain API order. So that means that the fragments, in the end, when they are blended by the raster output stage, they need to be blended in the very same order that the geometry was issued into the pipeline. And we already talked about what was called the work distribution crossbar when we talked about this work distribution phase in between vertex stage, primitive assembly, and scan conversion. And then we already saw that the granularity of the parallelism as it is exposed by the raster engines is quite different than the granularity of the parallelism exposed by the vertex processors. And we basically just said that there's a work distribution phase, and that it's important that we maintain API order so that those fragments that the raster engines generate have the same order that the input geometry had in regard to visibility. And the same is true here. Like, we again have a work distribution phase where the granularity changes. Like, the raster engines will just process like a handful of tiles, and there's actually only a handful of raster engines. And the raster engines will generate those fragment quads from those tiles, and then again we have a phase where we actually go wide, like a phase where we have this massive parallelism over all the warps, over all the cores, and over all the shader processors. And we should really briefly discuss how this would usually be implemented on a GPU, like how a typical GPU design would accommodate that. And by discussing this, we'll also conceptually understand how this is done on the other work distribution phase, like in the work distribution phase between vertices and raster engines. So the first thing that I want to mention here is, like we already saw, that all those concepts that I'm describing here, they are not rigorously published. Like there's actually a lack of research papers on all those topics. And this is because, of course, like we're talking about implementation details by the GPU vendors here. And therefore, the whole discussion kind of relies on those documents that are actually publicly available. And there's this one document that's called Scheduling the Graphics Pipeline. Like this is a set of slides by Mike Houston from AMD. And if I remember correctly, he also took those slides from another slide set from a talk by one of his colleagues who gave it at SIGGRAPH in like I think 10 years ago or so. And like there's actually a lot of great literature out there and like white papers that describe what's going on. And I want to point you to this particular talk here. Like you will find it on the internet when you Google Scheduling the Graphics Pipeline and Mike Houston. If you run a Google search for that, you will find the slide set, and you will find the slide set very informative. Like what I'm discussing in the following is like literally more or less word by word taken from those slides. And like you will find many of the concepts that I'm describing here, you will also find them described in this slide set, and therefore I want to like explicitly mention this slide set because you will find it very informative, and you should really look it up and have a look at that and skim through it, and so in order to like comprehend some of the things that I'm telling here. And the basic idea of the work redistribution phase is actually pretty simple. Like what we have is our raster engines, and those raster engines, they produce like a bunch of new fragments, right? And those fragments, they are then like dispatched to the fragment stage, and the fragment shaders that we have available are usually like many more. Like or each of those fragment shader cores can actually like process a bunch of those fragments that are now coming in, or of those fragment quads that are coming in, and it will like schedule them in words. And the question is really, how do we arrive on the other side? Like how do we go wide, so to say, without breaking API order, right? So we want to find a distribution of the fragments to the fragment processors without breaking API order. So how can we maintain API order? And the solution to this is actually fairly simple. Like what the hardware actually does, like what a typical design would do, like it's not said that each and every GPU would do exactly that, but what a design could do would be to just pre-allocate an output buffer and have that output buffer, of course, not be the size of the whole stream. Like we cannot just like possibly allocate another buffer where all the possible fragments go in. Like even if there's an upper bound to this, that's just not feasible. But we'll just pre-allocate, like for a batch of fragments, we pre-allocate a buffer, and then we just go wide. Like we distribute and load balance the various fragments that are in the current output batch from the raster engines. We redistribute them to the fragment shaders. Like, and I'm like kind of implying here that there is some type of load balancing, like, and that the assignment is kind of arbitrary. And we tag them like that we are later able to know where they go in the output buffer. And then we can work on them like asynchronously. Like, and then we will, every once in a while, we will like retire like a couple of fragments. Like here in this case, we retired 2 fragments and the other fragment shaders are still working, and then like we retire a bunch more, and each of them is tagged with the address in the output buffer, and therefore we know where to put it. And then in the end, we have a FIFO, and that FIFO, the raster output stage that follows the fragment stage, can work on in the correct API order. So this is actually a fairly simple concept, but this is actually like, this is the whole deal with GPUs, is that we have those small buffers. And you will remember back to our discussion about the rasterization algorithm, and we started with the rasterization algorithm, then we devised the rasterization 2 algorithm. And there we noted that in between those stages, like after the vertex stage, we have to store all the vertices. And then that would be followed by primitive assembly that would work on all the vertices and would output a large list with all the triangles, and that large list would go into the rasterization stage and into the scan conversion stage and into the raster engines. And then again, we would have to buffer all the fragments that were generated by the raster engines. And this is actually not how it works. And then what I later teased was that design where we have those small buffers, and we have those small buffers in between, and then we in a streaming fashion stream the data and the work through the whole pipeline. You always have batches of vertices, and those batches are processed, and then they become fragments, and then we process another batch, distribute the work, and go wide on those stages where there's massive parallelism, and then we have small buffers that can hold the output data. And this is actually the whole concept with GPUs. We have this extremely pipelined way of execution that is quite typical for how GPUs work. And I exemplarily illustrated this for the fragment stage, but it is conceivable that similar means are actually also employed on the scan conversion stage, that is at the work redistribution phase between vertex stage and scan conversion stage. Yeah, and here's all that again, on a couple of slides. And I again want to point you to this talk by Mike Houston and Aaron Liefen, scheduling the graphics pipeline. Really have a look at this talk because it's quite informative, and the slides are out there, and you will find them with a simple Google search. And this is basically all that needs to be said about the fragment stage. We're talking very briefly about the fragment stage here because all that needs to be said actually already was said. The whole concept of this wide execution and this massive parallelism on this stage is the very same concept that we also saw on the vertex stage. And then the only other thing that is noteworthy about this stage, with the stage being a programmable stage, of course, what is noteworthy is that when we work on those fragments in parallel, and we really want to work on them in parallel, this is a stage where we really want to redistribute the work in a way so that we can make use of this massive parallelism. The only thing that we need to take care of is that we maintain API order. And I just told you how this can be done. I just showed you an example how this can be done. And this is the most important things to note about the fragment stage actually, because most of what is important on this stage has actually already been said in regards to all the other stages. So, and with this brief discussion of the fragment stage, we will now go over to the final stage, which is the so-called render output stage or raster output stage, what it is called by people, and where what basically happens are the depth test. That is, if the fragments that we're talking about weren't already culled by a potential early z-test, and what also happens is alpha blending. And we'll now talk about this in a bit more detail. So in the raster or render output stage is a non-programmable stage, and it is the very last stage in the graphics pipeline, and it is responsible for the compositing operations. That is, it is concerned with determining visibility and with blending potentially semi-transparent fragments. The stage is also concerned with anti-aliasing, but we will not discuss this in this context. And then finally, if the color of a raster point was determined, then it's finally written to what is called the frame buffer. And the frame buffer can basically be thought as a dedicated memory region somewhere on the GPU, basically a staging buffer where the display processor has access and can access the data in order to finally output the data to a screen, to a monitor, to a display that is connected to the computer via HDMI, for instance. And the logic that is also implemented on this side is the double buffering logic is also implemented on this stage. And what I just described is true for a context where we really display an image to the screen, or where we have a display connected to the computer. And GPUs also support modes where we perform so-called off-screen rendering, where the frame buffer is not actually a hardware instance, where it is accessed by the display processor, but where the frame buffer is rather a texture that we're rendering into. Like the concept here is called an FBO, a frame buffer object, where we have a so-called color and a depth attachment, and those are basically like textures, and those textures are bound as like virtual frame buffers. And then we render into those textures, and the raster output units, they write into those two textures, and then we can later like bind those two textures in another context so that we can access them. So we're not necessarily rendering to an actual screen, but we'll like potentially also rendering to an off-screen buffer. And then we later use that off-screen buffer like in order to perform a post-processing step on it, or to render it to a texture that is like part of the scene that we're rendering, like where we have like some portal logic or something like this, where we can have a look through the portal to another part of the scene, for instance. So there's all sorts of options, and nevertheless, what the functional unit that is concerned with this is the so-called raster or render output unit. Like, this is not clearly defined what the abbreviation actually means. Like, people call it the like basically just call it the ROPS, and this stands for like either render output unit or raster output unit, and I will like use those two terms interchangeably, but they're like a fixed function type of hardware. They are non-programmable. They are still a parallel phase, like typical architectures like the NVIDIA Maxwell architecture, for instance, had like 64 ROPS. And at this point where the ROPS start operating, this is the very point where API orders like really required, where we have to make sure that the fragments that are now turned into pixels are passed to the ROPS in API order. So, and at this very stage where the ROPS have written their output to the frame buffer, like the render output is inside the frame buffer, and now the display processor accesses the frame buffer's context, things become a bit more interesting, because there we're usually in a bandwidth limited scenario. Like the frame buffer accesses, they usually happen asynchronously, and we usually have like very low latency requirements there, because the display will access frame buffer contents like with 60 hertz or even above, depending on the type of display that we've connected. And here, bandwidth and making good use of the available bandwidth is a really important issue, and therefore the vendors employ frame buffer compression. And the APIs, on the other hand, require this compression to be lossless. So, however the display processor compresses when data is written to the actual screen, the compression needs to be lossless and may not introduce any like rounding errors or whatever types of errors it might introduce. And for those reasons, we'll now have a brief discussion about several different compression techniques. Like here on this stage, the type of compression that usually comes to play is like delta compression and run length encoding and all those sorts of compression types, and we will discuss those very briefly. And we will also take this opportunity to discuss a bit about compression in general. Like the schemes that are employed by the GPUs are usually quite simple, and of course there are much more advanced compression techniques out there, and they are interesting on their own. So we'll have like a very brief discussion on compression techniques that are typically used for instance, for image data. And we will start with a very simple technique that is called run length encoding, and the principle there is just the following. And the principle is fairly simple, actually. Like, just suppose we have this array, like, let this just be an array of colors, but this could actually be anything, like an array of characters or of integers. But in our case, and for the illustration, let us just assume they're colors. And when we like encode those colors, like we would say, for instance, have 32-bit for each color, which is like quite common, like that we have a 8-bit per RGBA color channel, then we would be able to represent that array like in a raw format with 448 bits. And like with run length encoding, we would identify so-called runs. And like for this array, that I would see that the first run would be like a run of length 9, and the symbol that is referenced is just the color blue. And I can also see that there is a second run, like a run of length 5, and this run references the color red. So with that, I can just run length encode that array by just noting that the run length itself can be encoded with an integer. Like, let's arbitrarily say that this is also a 32-bit integer, which in general will be a different bit width than that we used for the colors, but just for simplicity's sake, let's assume that. And like, we can still encode the color with 32 bits, and therefore we can just encode that whole sequence with 4 times 32 bits, right? Like, we would encode the run length with 32 bits for the first run, and we would encode the color that is associated with the first run with 32 bits. And we would do the same with the second run, and that would, like, in the end, give us 4 32-bit integers or 4 32-bit data items, and that would add up to 128 bits. And this is less than the 448 bits that we encountered for the raw encoding. And this gives us a compression ratio. Like, the compression ratio would be like roughly 4 to 1, like 448 over 128 to 1. And the effect that this fraction here is greater than 1 tells us that this is a positive compression rate, so that we have been successful at compressing this sequence. And run length encoding is actually a pretty naive, simple way of encoding things. There are several reasons for that. Like, on the one hand, there is like a sequence that is inherent to this, and as such, it doesn't lend itself very well to like parallelization. So this is one thing, and another thing is obviously that we can have like compression rates that are worse than we would see with like a naive raw encoding. In order to understand this, let us consider just this sequence here. And if we were to run length encode that sequence, like, in comparison, of course, the raw encoding still stays the same, right? Our 448 bits don't change because we still have like 14 pixels in the row, and the colors are still presented with those same 32-bit. But the run length encoding is much more complicated because we now have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 runs, and each of those runs would be encoded in regard to the run length and to the color, and therefore we would like have to store 20 32-bit values, and this would amount to 640 bit, and this would give us a compression rate where this fraction here is below 1, and that's of course problematic. So this is not the only thing that is problematic about this type of compression, because like in general there are still certain like assumptions that people make about what the data looks like, and you quite often like choose a compression algorithm that is beneficial in many cases, and then if there are certain cases where it doesn't work out, then people sometimes are okay with this. So the biggest problem here isn't really the fact that we can have those bad compression rates. Like, there are other algorithms out there that give us better upper bounds. But a inherent problem here is really that this is inherently a sequential algorithm. Like, this sequence here is like really hard to process in parallel. Like, what people would usually do is they would run length encode like all the rows and then have parallelism in regards to the rows, where you have each processor decoding the run length encoding of each row, and then you have parallelism there. And you could also do this with tiles, like what I'm showing you here with a row can also be used for like columns or for tiles. But in general, this is of course a problem, that there's not so much freedom in how to process this encoding in a parallel fashion, and there are actually other algorithms that lend themselves better to parallel processing. So yeah, and here's just another example of run length encoding. Like, I'm not going to do this in detail, like it's conceptually the same that I just showed you. Here I'm using a byte representation of the data and not a color representation, but it's basically the same, and the run length encoding method is like, it's a very simple compression method, and it has its merits, and it also has its downsides, and it's still like it's like a primitive compression operation, and it's important to keep in mind how that works, and I will mention it from time to time. And apart from all its downsides, it has like also several advantages, and one of those advantages is that the compression is lossless, and lossless compression is actually pretty important, like in particular the GPUs when it comes to compression of the pixel stream that goes out to the display. This pixel stream needs to be compressed losslessly. And run-length encoding is a very simple algorithm, but the type of algorithms that quite often come to use are so-called delta color compression algorithms. So the idea is basically that if you have like a block of pixels, that you pick like one representative color from that block of pixels, and then compute for all the other pixels, you just compute the difference. And if the differences are relatively small, that is, if the variance is not very high inside that block, then you can potentially represent the difference with very few bits, like in comparison to how you would represent the base color. Like you would present the base color with the full pixel width, and you would represent the difference just with fewer bits. And if the variance isn't very high, this is actually something that is pretty viable. Like we still have to perform lossless compression, and therefore it's important that when we compress that difference with a certain number of bits, that is actually representable with that number of bits. Like we're usually assuming an integer representation here. So if we say we had 32-bit colors, then we would maybe aim for representing the differences with 8 bits. And then we have to make sure that the difference actually fits into that 8 bits, so that the difference wouldn't exceed that limit. And this is of course not always possible, and therefore GPUs usually employ heuristics. Like they start with relatively large tiles and try to compress them, and if they can't be compressed, they subdivide them further. And in the end, if a tile just cannot be compressed, then the GPU will just handle it in an uncompressed fashion, because it contains too much variance. And it's actually quite surprising how much bandwidth can be saved with this very simple approach. Like there are a couple of documents out there where you can find out more about this, and you will see that delta compression is actually used quite a lot, and there's a reason why this is used quite a lot. Delta compression obviously is most effective when it comes to color gradients. Like here I'm showing this at the example of a floating point representation with an image that contains only gray values. And as you can see here, the compression that I can apply here can compress this actually quite a lot. Like the base color that I'm using here is like this 50% gray. And then I can represent the whole row here with those differences in regard to the left neighbor with a difference of 0.1, right? And I could even run length encode that if I wanted to. And the differences in the columns there are no differences, and so I can represent them with zeros. So the compression that I see here is actually quite high, and you can see from that example that delta compression is actually most effective when it is applied to color gradients. And if you recall our discussion of how the scan conversion stage works, then you remember that there's a lot of interpolation going on there. Like on the scan conversion and also on the fragment stage, there's linear interpolation everywhere. Like this starts with the raster engines who interpolate depth and color over the triangle surfaces, and this uses barycentric interpolation, but effectively, in a row of pixels, the interpolation is a color gradient. Like the result is a color gradient. The same is true for texture interpolation. Like we usually employ interpolation inside those textures, and that means that those 3D renderings are dominated by those color gradients. Like those color gradients, they show up all over in that pipeline. Again, if you for instance consider it like a racing game, and then in that racing game you have a sky, and then it is quite likely that you can represent the better part of the upper half of the screen with a delta compression scheme where the sky is just a gradient, and you store a single blue base color somewhere and represent all the differences with way fewer bits. Like, this is actually pretty common, and in particular when you take into account how those phenomena are usually rendered. Like when one would render a sky, they would usually use some type of gradient for that, like maybe a texture, like a very low variance texture with containing like a couple of blues. And those exact phenomena are representable quite effectively with delta compression. And the reason here is really because inherently the GPU interpolates linearly across the whole pipeline. Yeah, and now I want to take a brief detour and discuss a compression algorithm that is a bit unrelated to like GPU processing, what is happening on the render output stage, but nevertheless the algorithm is kind of like a building block for other compression algorithms, and it's like a pretty versatile type of algorithm that is, in my opinion, pretty interesting to understand, and that fits very well into the discussion here. And it's an algorithm that is a bit more advanced than the algorithms that we saw before. And it's called the Huffman Coding algorithm. And it's similar to the simple algorithms that we saw before. It's a lossless encoding. And the idea is just that we encode information with as few bits as possible. And we therefore use a so-called variable length encoding. That is when we're compressing like a sequence of symbols, like a word over some alphabet, then we're interested in representing those symbols that occur quite frequently with fewer bits than those symbols that don't occur so often. And so here the question is, how is frequency defined? And frequency can be defined in either of two ways. So in one way to determine if a letter occurs quite frequently would be to build some type of statistic, like for example, like analyzing English text and then determining how often a certain letter from the English alphabet occurs in those like standard texts, and then assign a frequency based on that. So this would give us a very general notion of frequency. And then there's another notion of frequency, that is, we could also do the very same thing, like if we were to send a very long message, like say the message would be comprised of like a research paper or a small novel or something like this, that we could like specifically for the message count the number of letters and the occurrences of the respective letters and determine that statistic, but make it specific to the message that we send. So there are those two possibilities that we have, and the algorithm lends itself to both of them. And the algorithm has the same disadvantage that we also saw with the run length encoding algorithm, like that, as there in certain cases we can end up with a compressed message that is actually bigger than the uncompressed message. And the input to the Huffman coding algorithm is just an alphabet sigma, and then we're given a word W of length n over the alphabet. And then the algorithm consists of constructing a trie or a prefix tree so that each symbol in sigma is assigned a unique prefix. So in the procedure to do that is actually fairly simple. Like, we would first start with building a list of tuples, and those tuples would map each A and W to its frequency. Like, we have tuples where we have each symbol A that occurs in W, and then we would have its frequency. And like here I'm implying that the frequency is derived from W, like that we count how often it occurs in W. But we could also like use a statistic for that. Like this would have several advantages or disadvantages that we'll discuss in a little bit. But we'll just construct such a list. And then we have a list with such a tuple for each A and W, that is for each symbol that occurs in W. And then we would try to combine those pairs. Like we go through the list, and then we try to combine those tuples to pairs. And for that, we would just pick those tuples from the list whose frequency is minimal. And those two tuples we would use to form a binary tree. on that binary tree, which at those two tuples at the leaf nodes, and we would like arbitrarily assign, like for instance, assign the left subtree the maximum of the two, and then the right subtree the minimum of the two. And we would assign labels to the edges, like 1 to the left and 0 to the right. Like this is the convention that we're using here in this lecture, and we could also use a different convention. That doesn't really matter, but let's just stick with this. And so we now have a binary tree. Like when we start out with the list that we constructed in the beginning, then we would have a binary tree that consists of 2 leaf nodes. So then we would remove those 2 tuples from the list and enter a new tuple into the list, and that new tuple would basically represent that new binary tree. Like we would assign like a new symbol to it, like this combined symbol AB here, which is like a different symbol than either A or B. So we're getting a new alphabet here, really. And the frequency, we would just assign the sum of the 2 frequencies of A and B. So we would remove 2 tuples from the list and enter a new tuple. So then in the end, we have a new alphabet sigma dagger here. So then we would repeat that, like we would go back to 2 until eventually we have only 1 item left in the list that represents the whole binary tree that we constructed this way. And yeah, I'll just walk you through a quick example so that you get a better understanding of how that works. And for the sake of our example, let us suppose we are given the alphabet sigma that consists of the 4 letters A, C, T, and G. And we're also given a word over that alphabet, like we're given just this string here, like those bunch of letters that are from this alphabet. And now we want to Huffman encode that string, and for that we first assemble a list where we assign each of those symbols in the alphabet, where we assign that a frequency. Like we basically want a list of symbols A and of frequencies P of A. And like for that we really just count through the string. Like in the exercises we will see examples where those frequencies are given, so these frequencies can also be given, but in our case they're not given, but we have to derive them. We derive them directly from the string. And when we count them, then we see that like the A occurs only once, and the C occurs 6 times, the G occurs 3 times, and the T actually occurs quite often, like it occurs 10 times. And that's our first step of the algorithm. And then we try to find the 2 minima inside that list. And we can see that the minima are, in regards to the frequency, are A and G. And then we use those 2 and construct a binary tree from them. Like we arbitrarily put the maximum of the 2 to the left and put the minimum of the 2 to the right. And like if there is no clear maximum or minimum, we have to make a decision. But here things are unambiguous, so we can just decide which one to put left and which one to put right. And it's kind of an arbitrary decision, but we have to stick with it. And then we also, and this is similarly arbitrary, we put a label 1 that we associate with the left edge and a label 0 that we evaluate with the right edge. So, and this basically gives us a new alphabet, like an alphabet sigma dagger here. And that alphabet sigma dagger now consists of the C that we haven't handled yet, and of the letter T that we haven't handled yet, and that combined tuple GA. So when we now construct basically that list again by constructing it in regard to this new alphabet. Like we remove the G and A tuples from the list, and then we enter a new tuple that corresponds to G and A. Like when we enter that tuple, we assign just, as the frequency, we assign just the sum of the frequencies of the constituents of that tuple. Like in our case, that would just be the frequency of G and the frequency of A, and those happen to be 3 and 1, and we thus enter 4 here. And then we iterate on, like we again identify our two minima, and here they are, like C and the combined GA are the minima, and GA is smaller, so we put it to the right, and C is the maximum of the two, so we put it to the left, and then we again assign labels to the edges, like we assign a 1 to the left edge, and we assign a 0 to the right edge that we just entered. And then again, we form a new alphabet by removing the two symbols that we just handled, like the C and the GA tuple. We remove them and enter a combined tuple CGA with the frequency just assigned the sum of the two frequencies of the two tuples that we removed. And then we do this again, and now we have to like make a decision, because if we have an ambiguous case, and we basically just decide to put the T to the left, treat it as the maximum, and the CGA tuple to the right, and we again assign our edges, and with that we have constructed our Huffman tree. And we're basically done. And from the Huffman tree we can now read off the so-called Huffman codes. And the Huffman codes are really just the prefixes of the 4 symbols inside that tree. Like if we want to determine the Huffman code for A, this is just the code, the binary code 0, 0, 0, and this just corresponds to the prefix if we traverse the tree down to the letter A. And we can do the same thing for C, and then we will find out that the Huffman code is 0 and 1. And we can also do the same thing for G and for T. And we can now see why this is a so-called variable length encoding, because we're now devoting a different number of bits to each of the 4 letters in the alphabet sigma. Like in particular, we're devoting 3 bits to the letter A that occurs once inside the array. We're also devoting 3 bits to the letter G that occurs 3 times in W, and the 2 letters that occur more frequently, like the T that occurs 10 times, we devote only 1 bit. And therefore this is a so-called variable length encoding, and this variable length encoding allows us to relatively efficiently encode this string here. Like this is the original string that we derived the Huffman codes for, and when we encode that, like everywhere there is a T, we use 1 bit, and like the letters that occur less frequently, we assign them those 3-bit codes, and this gives us the overall encoding for this string, and like we can obviously now compute the compression rate. Like if we were to encode the string with a raw encoding, so basically no compression at all, we could represent the alphabet with 2 bits, right? Like we have 4 symbols, and therefore we require 2 bits. And that means like we have 20 symbols in the word W, and therefore we would have to devote 40 bits to this string. And in contrast to that, when we count the number of bits in this Huffman encoded string here, we will find out that there are only 34 bits. So the compressed sequence gives us 34 bits, and therefore we have a compression rate of 40 over 34 to 1. Yeah, and that whole example is also part of the slide deck that comes with the lecture, and here I'm just skipping over it, but it is the very same example with the same Huffman codes that are derived and with the same Huffman tree. And then in the end, where we encode the original string W, like that original word, over the alphabet sigma, and then we find out that the compression rate is 40 over 34. And you can also comprehend that from the slide set. So a couple of things should be said in conclusion. Like the Huffman codes have that property that the symbols that occur less frequently, they will be located at the bottom levels of the tree, right? So when we construct the tree, we insert those letters first that have a relatively low frequency, and then with that we basically construct the leaf level of that binary tree, and that will eventually result in the less frequent letters being located at the bottom of the tree, and the letters that occur more frequently will be near the root level of the tree, and this results in shorter prefixes for the letters that occur more frequently, and thus in fewer bits assigned to the letter. So, and another important property, obviously, of those Huffman codes is that we can uniquely decode them. And this is guaranteed by the property of the Huffman codes that no Huffman code is allowed to be the prefix of another Huffman code. And that allows us to uniquely decode those strings. Like when we go back to this encoded sequence, like we decode it from left to right, and then we encounter a 1, and we see that there's a unique encoding that is, as we so far only encountered a 1, there's really only that one letter, that letter T, that we can decode it with, because 1 isn't a prefix of any of the other letters, right? So in the very same way, we can decode all the other T's until we encounter a 0. And when encountering the 0, there are 3 candidates, and then we move further to the right, and then this leaves us with only 2 candidates. And then we encounter the third 0, and this leaves us with only the A. And as the A isn't a prefix of any other of the letters, we can uniquely decode it. And then when we encounter the next 0 and the next 1, we encountered a 2-bit string, but this 2-bit string isn't a prefix of any of the 2 3-bit strings, and this is an important property, and therefore we can uniquely identify that sequence 0 and 1 as the letter C. So this is an important property that Huffman codes aren't allowed to be the prefix of any other Huffman code in our encoding. And I'm not really gonna prove that this is the case for the Huffman codes, because it's kind of obvious, it just follows from the properties of the prefix tree that we just constructed. But for an intuition, let us consider a subtree with vertices A and B, and with edge labels 1 and 0, and those are at the top. And the very fact that they're at the top, that basically means that there is no vertex in A that shares a common prefix with any vertex in B. Yeah, this is really just the intuition. We have 2 subtrees, and no matter what is inside those subtrees, they could even be same. This is not the way that we construct them, but they could even be same. And then when we just add those 2 edges, 1 and 0 here, by adding them at the top, and this is the very way that we construct those prefix trees. Whatever we already constructed will go to the bottom level, and because of that, as we are adding those 2 edges at the top, we are guaranteed to have no common prefixes in the 2 subtrees that we just combined using those 2 edges. Yeah, and one final thing that is worth noting about Huffman codes is we saw that we can construct those frequencies either by inspecting the word that we're encoding, or we can just assume that the frequencies are given, based on some statistic. And there are different advantages and disadvantages to either of the 2 approaches. When we construct custom Huffman codes for the very string that we're encoding, then those Huffman codes are guaranteed to be a good match for that string, right? And in that very case, we'll also always have a beneficial compression rate. We're explicitly tailoring the Huffman codes for that very string. On the other hand, when we do that, then we also have to make sure that the sender and the receiver, the software that sends and encodes the signal, and the software on the other end that receives and then decodes the signal, they have to agree upon the mapping. And as they have to agree, when we use custom Huffman codes that aren't derived from some common statistics that are based on some dictionary or so, then we also have to send the Huffman codes along with the message. And now it of course depends on how long the message actually is. Like when the message is a novel, then it's probably viable to like send all the letters in the English alphabet along with the frequencies according to the letters that are used in the novel. And on the other hand, if we have like many shorter messages, then this might not be viable because the size of the encoded alphabet might be larger than the actual messages that we send. So if we want to use custom Huffman codes for the string that we're compressing, or if we base that off of some statistic, kind of depends on how long those messages are, and thus this depends on the actual use case that we're designing the Huffman codes for. So we've now discussed like a bunch of lossless compression algorithms, and we will now go over to talk about texture compression, and we will find that the algorithms that are used for texture compression are allowed to be lossy. And with the discussion of the render output stage, like the discussion that we just finished, we're also finished with this sequential discussion of the graphics pipeline. Like we've now discussed each of the sequential stages of the graphics pipeline, like when geometry and vertices are issued to the graphics pipeline, they go through the various stages that we just discussed, and we've now arrived basically at a final image. And the topics that we're going to discuss now are related to the graphics pipeline, and we will also have more discussion about graphics and GPU architectures, but the sequential discussion is now finished. And let us start talking about texture compression, and what we will talk about is so-called S3 texture compression, and this is a fairly old type of compression that was introduced with DirectX, like with a very old version of DirectX. And it's like actually supported by most GPUs. And it is a format that is highly lossy and that is optimized for fast decompression. So it doesn't matter at all how long it takes to compress those formats. Like this is always done like a priori and using some algorithm that is allowed to take its time. And GPUs nowadays include dedicated hardware for those very special 2D texture compression formats. And the formats, like namely the S3TC texture compression format, originally comes from a company called S3 Graphics. And then those formats found wider adoption when they were integrated into DirectX and was introduced as part of the DirectX ecosystem. But it is nowadays also exposed in the other APIs, like in OpenGL, for instance. And there are different variants of this hardware accelerated lossy compression formats, like the DXT1 and DXT3 formats. And the basic idea behind those two formats is that they work on image tiles, and those tiles are like assigned two base colors, and in between those base colors we perform interpolation, and the scheme that is used for the interpolation is very particular. So the basic idea behind those simple texture compression formats is actually pretty simple, and what I'm giving you in the following is not a recipe or an algorithm to construct this encoding, but I'm only describing what the encoding stores, like what the encoding looks like. We will discuss in a little bit like some ideas how one could construct such an encoding, but this is not what I'm showing you here, but I'm basically just showing you what the encoding stores. And the idea behind the encoding is that we encode whole tiles of 4x4 image texels, like this tile of image texels that I'm showing here. And then the DXT1 format that I'm exemplarily explaining here, like this is the RGB format of the two S3 formats. The DXT1 format would store two representative colors, like two base colors, color 0 and color 1. And the DXT1 format also stores codes per each image texel. And those codes might appear a bit arbitrary, like codes 0 and code 1 are pretty obvious. Like code 0 and code 1 we would assign when the texel just exactly has the value of one of the base colors, and then we would assign either code 0 and code 1. And for all the other texels, we would assign either of codes 2 or 3, and this would depend on which of the two codes the algorithm, the construction algorithm that we use, finds that it best represents the color in terms of the two base colors. Like you can see that the codes allow us to obtain the reconstructed color using an interpolation, like a very simple type of interpolation of the two base colors. And our construction algorithm, however it would work, would try to find codes that represent the actual color of the texel most faithfully with respect to the two base colors. And you can already see that it is extremely simple to reconstruct a texel. Like, given the two base colors, we would really just interpolate, like we would look up the code and then apply one of the interpolation formula. And this is where those formats actually strive. Like, a hardware implementation of this reconstruction is just very simple. Like, we would have a very simple hard-coded interpolation hardware where even the fractional value that we use for the interpolation is hard-coded. Like, we would divide by 3 or divide by 2 in the interpolation, and the fractional value would not depend on any distance between colors, whereas we are usually used to when we perform linear interpolation. So reconstruction is like really easy given those codes. And the compression that we achieve with those formats is also very good. Like, we would represent the two base colors with an RGB 565 tuple, so 5 bits for the red channel, 6 bits for the green channel, 5 bits for the blue channel, and we would store 2 of them. And then we would represent each of those codes with 2 bits, because that's just the number of bits that we need to encode a value between 0 and 3. And thus we would end up with two 16-bit colors and with 16 2-bit codes, and therefore we would be able to compress that whole tile with 64 bits. And this is actually a pretty beneficial compression rate compared to if we were to store this tile with a raw representation. Here's just another illustration of what this format is actually comprised of. Like, we would store 2 base colors, and then we would store a bitmap containing those codes that represent the interpolated colors. And of course, this is a lossy format. I mean, this is pretty obvious, and it's actually a highly lossy format. That is, like, if we were to compare with 24-bit RGB colors, like, which would be a very typical raw encoding of a typical color texture, then we see a compression rate of 6:1, which is actually pretty good for an image compression format. And we already discussed the DXT1 format, so I'm not going to repeat this here. And so the DXT1 format is able to encode 4x4 blocks of RGB texels. And there's also another format called the DXT3 format, and the DXT3 format would in a very similar fashion encode RGBA tuples, so could also encode an alpha channel. And with this encoding, the basic idea is very similar. Like, there are also codes and base colors. The codes are a bit different, of course, and in the end we end up with 128 bits per tile and not with 64 bits per tile, and with a somewhat lower compression ratio, but still with a very high compression rate of 4:1 compared to a 32-bit encoding of the RGBA image. So, and while decompression with those S3 texture compression formats is extremely simple, compression unfortunately isn't. Like, compression is actually particularly difficult. Like, what we basically have to do is we have to solve an optimization problem where we find base colors and codes that minimize the distance to the actual color palette. And the methodology that usually comes to use here comes from linear programming. And when usually employs some type of heuristic. Like this paper by Castaño that I'm linking you here on high quality DXT compression using CUDA has some pointers how this is done in practice. And the basic idea is that you fix one of either the indices or the base colors. Like you would, for instance, like determine a sequence of indices, and you would do this maybe randomly, like so that you have some indices, and then you would determine base colors that best fit those indices. So the codes are given, and then you only find base colors, and with those base colors you would uncompress the whole bitmap and compute the distance of the colors that you retrieved that way. And then you would repeat that for a bunch of other sequences of indices, and finally stick with the sequence of indices that minimizes the distance. Like generally, what you have to solve here is a linear optimization problem where you want to reduce the distance of the compressed colors to the actual colors in that tile that you are actually compressing. So, and with that, I'm ending today's session. Like today, we talked a lot about algorithms that operate in some type of image coordinate system, like in a 2D coordinate system. Like we talked about fragment processing, then we talked about raster output, and all those were related to 2D. And now our final discussion on compression formats also basically implied that we're in a 2D coordinate system, like at the very least when it comes to the delta compression and the S3 texture compression formats. And in the next session, we will finish off our discussion on GPU architectures. Like we will talk about an assortment of different architecture-related topics. And I'll finish the architecture discussion in the next session, and hopefully I will also be able to already start with a discussion on actual programming for GPUs. Yeah, see you then.